Okay, hello everyone. Thanks for coming to this talk today by Chris Holt. He's a master student at the Technical University of Berlin, and he joined us for this summer to work on the strategic internship project on spatial audio. And his talk today is going to be about Ambisonics rendering. So with that, Chris, the floor is yours.
Thank you. Thank you, Hannes. As Hannes already mentioned and introduced, this talk will have a strong focus on Ambisonics, or the spherical harmonics domain. And in principle, we have real-time constraints. We want to be as efficient as possible. And what that means, I'll tell you in the next hour, probably. And okay, so let's consider for now what we face nowadays is usually all these new 3D sound systems, like spatial audio systems. We want to be able to reproduce sounds from all directions, from all 3 dimensions, and ideally we want to render hundreds of sources. So in the easiest case, that would be a very complex piece of music, but maybe more relevant nowadays would be game audio, for example, with a lot of sources, reflections, reverb, and everything. Or in our specific case, we have the augmented reality devices, which should be able to render a lot of sources as well. And so this would be the broad perspective. And since I already mentioned the augmented reality devices, we have a lot of constraints about the processing power on these devices. So let's see what we can do about that. So to render sound sources in general, we have state-of-the-art techniques, let's say. The most basic way would be we have our input sources x here, x1 to xn, multiple sources. We are here in the time domain, for example. And the easiest way to render those would be we have the filters h1 to hn, which describe the transfer path or the direction that we want to render, and the operation that we have to do would be a convolution in the time domain. So everything that is expensive I marked here in red. Well, the addition is not really expensive, but what really scales here is the convolution with our filters. And we have to do that per source. So the more sources we want to render, the more convolutions we have to apply. Even if we do some tricks in the frequency domain and everything, this is still expensive. And I'm assuming right now I only see audio people here. Everybody knows what an HRTF is. So okay, so here the H's are the filters are the HRTFs, HRIRs actually in this case. So this would be the time domain approach. A bit more state of the art would be the Ambisonics approach. What we have here is we feed our input signals x1 to xn to a encoding stage, and we obtain our spherical harmonics coefficients, which are always marked in this talk with nm, with the subscript. And so our input stage to our rendering is this big matrix of a lot of coefficients xnm. And actually what we are facing in reality is that usually this encoding stage is already done for us. So for example, the newest generation YouTube, as far as I understood, they transmit third order ambisonics already, something like that. So they already deliver this big matrix here, so to speak. So what we have to do now, or what our task is to be efficient or to render that, is here this rendering stage H, which would be the HRTFs in spherical harmonic representation. And there's an interface in between. And I will show you later that it turns out that this is only a linear combination of coefficients. So that means this does not scale with the number of sources, but it scales with the order, or let's say for now with the accuracy. So we have a tuning parameter where we can say we want to be more accurate, so we spend more coefficients here on the rendering side, or we say we want to be more efficient, we spend less coefficients, but we will introduce an error. So what that means, I will show you later. But let's keep in mind for now that we have these two paths, either in the time domain with convolution or the actual straight rendering process in the Ambisonics or SH domain. And the scope of this internship would be, since we already have probably the input matrix X, that we tackle this stage here, the decoding stage, and I marked it in green because we want to be as efficient as possible, right? So ideally no real-time constraints or no real-time, let's say, rendering or processing. So what is our input signal? Just to remind you real quick, this I think is a pretty cool picture. That's how you can measure all these HRTFs. Here we are dealing with full spherical HRTFs. So not only in the horizontal plane, but also, like as I said, the full sphere. And here you see the loudspeakers, and you measure the transfer path from a loudspeaker to the listener, and the whole thing rotates, and what you get in the end is the full representation of the sphere. So
where is that?
This is in Berlin. Yeah, I don't have a picture of Redmond, so yeah, a similar setup, right? But I don't have a picture, so that's the one I had. Yeah, so let's see again what happens in the time domain. So as I said, we have the convolution operation here. To obtain the output signal Y for one ear in the time domain, we convolve the input signal S with the HRIR for that ear and that specific direction or angle. In the slides that you see, I always use capital omega for azimuth and elevation, or colatitude actually. So this is how these HRTFs look like, and you can already see that this is not a trivial correspondence between angle and HRTF, so these are pretty complex, and they change over the angle quite a bit. So there are some approaches to approximate them and make them maybe a bit easier to represent and all that, but we're not looking at this scope. We are dealing with the actual HRIRs. So if we now look at the spherical harmonics domain, first of all, the SHT would be the spherical harmonics transform. So the way to go from the time domain to the spherical harmonics domain. And here in the simplest case, I just encoded, so to say, this HRIR in the spherical harmonics domain. And this would be this operation. And then to obtain this one time domain signal again, we would evaluate this integral over the spherical harmonics basis functions, and we would obtain just the HRIR for that direction. So this would be just a different representation of this. So we still have the convolution operation here, which we don't like, but we can do one or two smart things. And first of all, we transform the input signal S to the spherical harmonics domain here, and then the HRIRs to the spherical harmonics domain H. And it turns out we can say that to obtain the actual output signals for left and right ear in the time domain, it's just a linear combination of the coefficients. There's some math involved, just take for granted here that it works. And if you, just to remind you how these spherical basis functions look like, so this would be the 0th order, one coefficient. The polar pattern is just an omni. And then if we increase the order, the polar patterns get more and more complex, so we can render more complex spatial sound fields in space. But you can already see that this scales quadratically. So when we increase the order, we scale the coefficients that we need quadratically. Right. So as you can already see, to evaluate the whole thing, we would need to evaluate until infinity. So we would need an infinitive amount of coefficients to be perfect, to be so that we don't introduce any error. So what people do in practice is that they order limit the reproduction sum to some order n. And this looks like that. So you have some function f in the spherical harmonics domain. So these are the coefficients. And it is in the end a Fourier series. So for a given angle here, this is what it would look like if you limit the order to 5. You would have this polar pattern, and as you increase the order, you get more and more precise in the beam pattern to that specific direction. So if you look at that, if you go to infinity, we would in the end obtain the perfect spatial Dirac, which would be just the time domain HR, IR, right? Okay. So the problem with that is it's nice that we can just limit the coefficients and we introduce some spatial error, obviously. The problem with that is, though, we will not only introduce a spatial error, we would also introduce coloration. So a signal obtained from spherical harmonics of 5th order will sound very different than one obtained from 30th order. And this is what we want to ideally minimize, because we want to be as close as possible between time domain and ambisonics domain. So yeah, okay. So this plot will be interesting later. So I'll just show you real quick. These are the exact same orders from 5 to 30, and I just plotted now over the sphere. So you see, for one elevation angle, 90 degree. So for just the median plane, you see here from 0 to 360 degrees. So around you, so to say, around the sphere. We have the main lobe here at 111 degree. And if we limit to 5th order, we have the blue curve over the sphere, and you can already see all the ripple on the sphere that you also saw here, right? This is the main lobe, and then you see all these side lobes. And even with 30th order, I think it's pretty amazing that the first side lobe, or the most prominent side lobe, is still at minus 30 dB. This is not a lot of suppression, actually. I was pretty surprised when I saw that. Yeah, so let's see what we can do about that. Let's look at the problem. As I said, we want to limit the reproduction accuracy in terms of SH coefficients, and then be as close as possible to our reference, which is the time domain, and to look at the general error, the average error that we make, so to say. We can have a look at the common transfer function, which would be just an average over the sphere of all transfer functions. And what you see here is a frequency response in dB of the actual difference between the domains, between the time domain and the spherical harmonics domain. So ideally, we want to be completely flat here, 0 dB. If we are flat, that means we don't do an average coloration error. But you can already see here for 3rd order, so these are 16 coefficients, 16 channels, so to say. We start losing high frequency content at above roundly 2 kilohertz. And the problem is that we go all the way down to minus 20 dB, even a bit more than that, which would mean if we would switch now between the SH representation and the time domain, this would be super dull. Like, we would miss a lot of high frequencies. And as I said, we have a tuning parameter, so we can just increase the order a bit. Here we are already at 8th order, so we already have 81 channels. We're doing quite a bit better, so the aliasing frequency goes up quite a bit, but we still see that we are missing 15 dBs in the highs. And if we crank to 15th order, it's again getting a bit better, but remember that it scales quadratically, so this is a lot of computation necessary here already, and we still have an coloration in the high frequencies. So not only that, if we now look at actual HRTFs obtained for specific directions, so not at the average, not at the common transfer function, but for one specific angle. Here, for example, would be just right in front of you. You would see this high frequency loss again. But as we move in the azimuth in 45-degree angles now, you can see that this changes. So this looks already quite different. This would be 90 degrees to your left. So you can already see that the left and the right ear don't look similar anymore. And I would even say, in this case, for example, which would be slightly behind you, we are actually not losing high frequency content anymore, right? This looks, I mean, there's quite some ripple, but the minus 20 something dB that we are missing here are kind of gone. So from that, we can probably conclude that just a static filter is not enough, right?
So what's the explanation for why that varies so much over the azimuth?
Yeah, that's a great question, which I will tackle later. Yeah, if that is okay for you right now, I will just explain that later. But yeah, let's keep that in mind, that it's very order dependent and also angle dependent. That's the takeaway here, I would say. Okay, so solutions. Let's first of all talk about the state of the art. This is a very recent paper, as you can see, which tries to tackle the average error that we make. So the common transfer function where you saw that roll-off. This is what they try to tackle here. So the average coloration, so to say, that we introduce when we truncate the reproduction order. And I will come to that, how you can derive that later. But let's just take for now the only thing that we have here. Okay. First of all, we are assuming a spherical scatterer. So we are modeling the human head as just a spherical scatterer in a diffuse sound field. And then we look at the average transfer function or the average response of that sphere in terms of frequency. So we just look at the frequency response of the sphere, so to say. We look at what happens if the sound field hits the sphere, how does it propagate over the sphere, so to say. So we have the wave number k here, and it's only dependent on the radius of the sphere and the order, which is nice for us. We will see why that is nice later. So what it is in the end, that is just a weighted sum of the mode strength of the rigid sphere. And this is solved analytically. So we can actually derive the perfect, or the actual analytical solution of the sound field on a sphere, dependent on the order and dependent on the radius of the sphere, which is very nice. So we know what will happen if we introduce a spherical scatter to a diffuse sound field. And this is how the mode strength looks like. This is the B here, that we then sum to get the pressure field. You can see here that the response for the 0th order is kind of flat, and we lose low frequency level as we increase the order. But if we then sum them all together, we get the actual pressure on the sphere. So this is what we are interested in. And you can see, as we increase the order, the roll-off where we start to lose high frequencies increases. That's exactly what we already saw in the common transfer function, right? So turns out that the spherical model for this basic diffusive field is actually very good. It's very robust, and in that paper that I just showed you, they also analyzed that this is a good model to obtain the frequency response. And what that means here in this case is, let's say you have a spherical harmonics representation of 3rd order, and you want to make it sound like it would have been a 30th order. So you can just, if you look at this graph, you can just crank the high frequencies a bit, and then the overall diffuse field response would be compensated. And this is exactly what we can do. So in our case, for our model, it turns out that we need 38th order to be completely aliasing free, so that we don't introduce an error on the sphere. And now we can obtain these filters to compensate for this high frequency loss. So it turns out for the 0th order, we need this filter, and we are probably more interested in something like the 3rd order maybe. That's like a good default maybe. And we see we have to boost quite a lot, over 20 dBs, to compensate the loss that we introduce by truncating the reproduction order. But the nice thing is we can actually derive the filter. Good. So great. But as you remembered, just cranking the high frequencies is probably not enough because it's so angle dependent, right? That's what we saw earlier. So we had a look at that. Well, I just walk you through real quick in case you're interested. So we start. So how we obtained it? I mean, so we want to obtain the pressure field dependent on the angle and dependent on the wave number. And we start here just with a very basic formulation of the inverse spherical harmonics transform, which is just a Fourier series, as we already saw. Here with the spherical basis functions and some coefficients of the sound field P and M. And now we throw in assumptions. Okay, so first of all, we are assuming the spherical scatterer model that we know the analytical solution. And so this P and M now is described as some weighting coefficients A and M, which are dependent on the order, and these mode strengths that you already saw, B. Then we are only interested in the relative difference, so we assume a unit plane wave, which simplifies it quite a bit, to only the mode strength, and then the spherical basis functions. And then we can simplify even more and say we can obtain the whole frequency response of the sphere for an angle only dependent on the truncation order. As this thing here, it's like, again, a weighted sum. This is like a Legendre polynomial. Doesn't really matter in our case. I will show how this looks like, but let's just keep in mind we can actually derive the frequency response of the sphere just dependent on the order and the angle. So we can just play around with these parameters and then compare, so to say. This would be the frequency response of the sphere now. So remember the nice behavior that we saw earlier. If we actually look at the angle-dependent frequency response, it looks quite different. What I plotted here is just in 10-degree steps around the sphere. So it doesn't really matter which angle is which, just we can already see that it's highly angle dependent. And well, this is minus 20 dB here, and this is more than 6 dB here. So this is a difference of 25 dB that we introduce. And we look here at the left ear, and I think that the most basic explanation is we have the spherical scatterer, we look at the left ear, which we place on the sphere. So if a sound source is coming from the right, it gets scattered and occluded by the sphere. So what will happen that we will introduce a high frequency attenuation, right? So yeah, and that's what we see here. And it's derived analytically, so it's nice to calculate. And this is the full spherical bandwidth, 38th order, as I said. Here we assume that we don't introduce any error. You can actually see that we start right here at aliasing frequency, time frequency, that we see some weird behavior. So we are right at the edge where like 38th order is probably the minimum. But then if we truncate to third order, which we are actually interested in rendering, this thing looks like that, very different. And this is what we actually have to equalize now. So you can already tell this is going to be a hard procedure and a pretty sophisticated job. And just to tell you real quick what we did, we took this frequency response here, third order, and then first of all, we applied the static offset. So we already know what the average error is that we introduced by third order. So we apply that, which would be this 25 dB high frequency boost. And then the remaining difference for the angle-dependent filters would be this. So this is what we still have to add on top of that to actually compensate it, dependent on the angle. And well, it turns out this is probably not feasible for us for multiple reasons. First of all, you can see how highly angle-dependent that stuff is. So it's very unstable over the sphere. Then you would need to spend a lot of coefficients to actually render it, these frequency responses, to get the filters. We tried different stuff of smoothing on the sphere, averaging on the sphere, smoothing in time frequency domain, all kind of different stuff. Turns out it's just not. It's not really a good idea to be that precise in the angle, let's say, and like try to compensate every single angle and all that stuff. And on top of that, there's another problem. So let's say we can somehow derive these filters for every angle. How do we apply them? We have to apply them in time domain, which means we have to apply it for every single source and add another filter on top, which is a convolution in worst case. So we're not gaining anything really. We get more accurate, but we are losing performance like quite drastically. So we can actually just render it in time domain then probably and be more accurate, and it's probably easier and everything. So yeah, this is something to figure out maybe for somebody else. It's there. It might be a direction worth going, but we stopped at this point and tried something else. So in the end, the basic idea now is, how do we tackle the angle dependency? And I can tell you right now, we tried tapering in the space frequency domain. So I'm pretty sure that most of you are familiar with the time frequency domain, and that if you have a window, it's probably a good idea to taper the window to get rid of side lobes and everything, right? So pretty much the same thing applies in the space frequency domain. So first of all, what is a window? It's pretty simple actually. In our case, let's say we now, for this example, I crank the order now a bit to 5th order so that we have at least 2 coefficients to play around with. So it turns out the window here, a Hanning window, would just be weight the 4th order, so the 5th coefficient, to 0.75 and the last coefficient to 0.25. That's all you have to do. It's that simple. Took us 3 months to figure that out. And what happens now, if you remember the plots that I showed you earlier, this is the side lobes on the sphere that the current state of the art, let's say, produces, which would be in signal processing terms, that would be just the rectangular window, right? And we have that massive side lobe here with minus 15 dB. And if we apply just these 2 coefficients, we get completely rid of that. I mean, less than minus 40 dB. Of course, it's still there, but it's very, very quiet. And we can reduce all the side lobes here too. Well, the trade-off, as always, is that we broaden the main lobe a bit. But, I mean, that's like, I think that's acceptable, right? It's like, I would say that looks good just from the plot. Right, so this is what we did. Now the important step is, though, when we play around with the weighting of the orders, we will introduce another coloration error, right? So when we truncate the order with a rectangular window, we apply the diffuse field filter, for example, to compensate for that basic or that average coloration. So what we did now is that we introduced the window to this filter. So we tell the filter, we apply the window, compensate for the average error of the window too. So this is the state-of-the-art diffuse field compensation filter, just added with the window, and all that happens is really that you boost a bit more. That's all that happens. It's like a couple of dBs. It's really not a big deal, and you can compensate for the coloration introduced by the window with that. So, how does it sound? I brought you some examples. Let's see. So remember, first of all, our reference is the time domain, right? That's what we want to achieve in the end. The time domain is the perfect render for us right now. So what I did here is I have a snare drum signal, so a very critical signal, so to say, an impulse, high bandwidth, and it starts right in front of you and then just goes in 10-degree steps around you. So these are the binaural signals played over loudspeakers. That doesn't work, of course, but you can still probably hear the coloration. Because I will switch between the different conditions now and the time domain. And of course, like the spatialization wouldn't work for you, but you can still pay attention to the coloration. And what you will hear is here, down here, you can actually see it, right? Yeah. So down here, this is T, this is the time domain, this is our reference. And then here, up here, it's 5th order, as I said. If we just truncate the order and do nothing, let's say state of the art, this is the render up here. Then if we introduce that basic coloration filter, that diffuse field filter, that would be the next render. And then if we, on top of that, apply the tapering approach, this would be this guy here. And pay attention to the high frequencies and how they change over the angle. This is probably what you want to listen for. Yeah, just to help you a bit with the setup here. I actually brought headphones so we can listen to it later in like full fidelity, let's say. All right, first of all, the time domain signal. And it doesn't work anymore. Too bad. Here we go. All that matters here is that it's a pretty smooth movement and there are no jumps or anything, right? Just take that for now. Now we truncate to 5th order, 36 channels. Yeah, you hear all that high frequency loss, the weird angle dependency. Now, if we compensate for the high frequency loss with a static filter, well, we get some high frequencies back. That's what we expected, right? Oh yeah, sorry, I'll switch. Yeah, that's the diffuse field filter that you saw, the state-of-the-art filter, where I gave you the reference, so to say. This is like the latest compensation, so to say. Yeah. Yeah, you have to listen to that via headphones. Just pay attention to the coloration, maybe. I'll switch between time domain and this right now, back and forth. So this is SH, time domain. Not too bad. But yeah, there, for example, you heard that it's way too much high frequencies on the sides. That's what we expected, right? Too much high frequency boost. And now with the tapering approach, you should hear, I'm not sure if you can hear it, but you should hear that it's smoother over the angle, and we don't have that crazy high frequency loss. Well, it's still not perfect, right? It's always a trade-off, but you have to listen to it more critically via headphones, but you can clearly tell the difference, which is amazing because all we did is like change 2 coefficients, right? That's all we did. Okay, let's listen to that more in detail later, maybe. Okay, let's have a look at what actually happens. So I will introduce you now to a few things that we did to analyze. I'm not sure if everybody's familiar with the gamma tone filter bank, probably, right? It's like a psychoacoustically motivated filter bank that kind of mimics what the ear would probably resolve in terms of frequency resolution. And if we look at the level difference that we introduce when we order truncate between the reference and the order truncated signals in these frequency bands and then average over them, we get one value here in dB per angle, right? So what you see here is the azimuth from 0 to 2 pi and the colatitude from 0 to pi. And you get one of these nice pictures, and we always look at the left ear. So here, this would be the ipsilateral side, so a sound source coming from the left. And this would be the contralateral side, a sound source coming from the right, if we look at the left ear.
It's the difference with the HRTF, not with the spherical.
Oh, yes. Sorry. Yeah, this is the actual HRTFs. Exactly. Yeah. So this is the actual thing that we render, that we listen to. Yeah, and just this is already with the diffuse field compensation filter. So this is, so to say, the latest state of the art, where we already compensated for the high frequency loss. And you can see that it's not too bad. It's 5th order already, though, right? It's already quite a bit of data that we need to obtain these. Yeah, but we go always up to 10 dB here in the ipsilateral side, and yeah, I mean, as you could hear, it's pretty angle dependent, all that, and you know, it is a problem. So this is just to look at it. What happens if we now apply the tapering? It looks like that. Now you can decide for yourself if this is better or worse, but it's definitely more smooth, right? That's all that matters for us right now, is that actually the ipsilateral side, there's not much happening. It stays almost the same. But in the contralateral ear, where all the aliasing occurred, we get quite a bit of, I would say, better response, at least smoother response. So again, this is without tapering, state of the art. This is with tapering. If we now look at the actual frequency, let's say frequency dependency, I split it here in 3 bands just to analyze it a bit, or to visualize it a bit. The first band would be up to 1 kilohertz. So this is where we don't expect any error, because this is below aliasing frequency. The second one is between 1 kilohertz and 5 kilohertz. Still auditory bands though. And the lowest one here is a plot of everything above 5 kilohertz. And pay attention to the scale too. Unfortunately, I had to scale it a bit so that we see anything. So yeah, this is dB. So we don't have pretty much no error below 1 kilohertz as we expected. And then without tapering again, right? But already the diffuse field compensation filter, we can see here this spike in the contralateral ear that we also could hear. And this is always compared to the reference. So we see that we are too bright here in the contralateral ear. And this gets even worse if we increase the frequency, the spike here. So this is up to 20 dB, right? This is the error that we make. It's 20 dB too bright, so to say. And also like some coloration here on the ipsilateral ear. But yeah, well, that's what we started with. And now if we apply the tapering, you can already tell that we get a lot smoother. And now again, pay attention to the scales. Here it stays the same, right? But here, this is 10 dB and this is 5 dB. So you can see that we get rid of that guy quite a bit. And then here in the high frequencies, even more, right? So this big bump here is almost gone in this representation here. So I would invite you again to listen to it via headphones. It's pretty cool, actually.
So it looks like the ipsilateral stays pretty much the same.
Yeah.
That is the contralateral that really can.
Yeah, exactly. That's how I would describe what happens. Yeah, we smooth it, so it's a trade-off. But where we care, the ipsilateral side stays the same. We only improve on the aliased contralateral side. So this was all in frequency domain, right? So transfer functions. If we now look at the actual time domain, we see something very interesting as well. So this is without any tapering. The time domain, HRIR, the impulse response, here in blue, for the left ear and for the right ear. The angle is, I think it was 111 degree again, like somewhere here. So you can see the time offset, and you can see the level offset, right? And what you can also see is all that aliasing that we introduce here in the SH domain. So it almost looks like quite a bit of the left side render aliases into the right side in time domain.
Sorry, say again what are we looking at?
This is the impulse response of the head-related impulse responses. And we look at the T at the time domains and on the render of the SH domain, 5th order, for the left and the right ear. So ideally, we want to match these two lines as close as somehow possible. If they would match exactly, it would be the same impulse response.
So T is the ground truth reference.
Yeah, exactly. Yeah. So we want to match the dashed line to the blue line.
That's true, but there are maybe dimensions of matching that are more important than others, I think. What's critical here is you've lost all the ITD and
Exactly.
If you kept the coloration error, but then at least fixed the ITD, that would be a huge improvement perceptually.
Yeah, that's why I show it here. So we only had a look at the time frequency domain so far, but if we look at the actual time domain now, we can also see quite a bit of aliasing that we introduce, right? So looking only at the transfer functions is fine to observe coloration, but there's also stuff happening that we can see more clearly in the time domain. So this is without tapering. Now look what happens if we introduce the tapering. It's quite a bit better, isn't it? And if you also pay attention on what it is, so this is a lot of high frequencies, presumably, right? And this is like a low frequency bump. And then we actually match quite good here in the HRR that we want to tackle and that we want to match. So we're even improving on that as a side effect, so to say. Well, in the end, it all comes from the side lobes, right? So if we, yeah, well, you saw it. All right, this is just something that I wanted to mention and I wanted to show you. To have an objective measure for all that we now listened to and looked at, we applied a pretty sophisticated binaural model. And we can go into detail maybe later how we came up with these numbers. But let's just say for now, what we see here is the coloration that we introduce over the angle, some relative measure, let's say dB for now. And of course, if we can compare the time domain to the time domain, well, there's no coloration, 0. But then if we look at the order truncated versions, we can see that here for the angles of 90 degrees, so to the sides, we have quite a bit of coloration here, and also on the contralateral side. That's what we already saw in the plots, right? But this is now an objective measure, like a well-established binaural model that also tells us, look, you have coloration that you introduced here at these angles. And we were able to smooth these out quite a bit. So the purple one is the tapered now, the tapered version. This is already 5th order, so it's actually not too bad, right? I show you 3rd order later, where you can see it maybe more clearly. I'll show you that now. So 3rd order would be just put the last coefficient to 0.5. Ta-da! And what you do with that is that you can actually suppress this side lobe still quite a lot by just applying this one coefficient. And then, of course, you have to compensate in the frequency response, right? But that's all pretty simple. That's all offline. We can do that before we even start the rendering. And now look at the coloration plots again. This is a bit more easier to see, I would say. Again, blue is the reference. And then compared to the reference, the 3rd order signals, when we just apply the truncation and do nothing at all in orange here. So you can see quite some severe distortions in the front and in the back. Then if we apply the static diffuse field order compensation filter, we shift the error kind of. So in the front, it's now pretty good. It's like, yeah, it's decent. It's 3rd order, right? Only 16 channels. But we have all that error to the sides now. That's what we already heard, right? All that high frequency boost, kind of. And then if we, on top of that, apply the tapering, we can smooth this out quite a bit. So look at all these crazy spikes here. It's pretty decent, I would say, right? It's like, looks pretty steady over the angle. Well, we have some coloration, of course, it's a trade-off. But it doesn't jump with the angle. So it's, I would say it's way less perceivable for the average consumer or audience than if you have something that changes coloration over angle, because like this is very audible and very obvious to pretty much everybody. Okay, that's it. That's all I have to tell you for now. I guess now it's worth trying it out and maybe try different representations. There's a lot of stuff that we can still tackle. So far, we only tackled the reproduction side, right? Only the decoding side. But maybe we can improve also in the encoding side. And well, it all depends on one each other. And we already saw some new, let's say, techniques, how we can probably improve the encoding already. So we probably will do way better on the decoding then and all that stuff. That's maybe the outlook that I would have to add here. And of course, I think we should, or people should maybe at least try it. It's so simple. It's like, just wait it a bit and you're good. Like, I actually played around with very sophisticated window functions and tapering function, all that. It doesn't really make a difference, honestly. It's like, just apply some window. Like, not a rectangular window. That's better than everything. If it's a Henning or Hemming or some super sophisticated whatever window, it's like minor differences. Doesn't really matter, I would say, at this point. I mean, we're only talking about a couple of coefficients, right? So the actual window doesn't make a difference, I would say. All right, that's it. Thank you very much. Had a lot of fun, and even if it looks like my mentor didn't, but yeah, it was pretty cool. All right. Yeah.
I have a couple questions. So just to make sure I'm understanding the tapering correct, you take, for third order, you would take all the third order components, so there's 16 channels, so the last, is it 5 channels? Those are what you're applying the tapering coefficient to?
I just weighted them with 1/2.
Yeah, just divide them in half.
Yeah,
okay.
That's all.
Okay. Yeah. So the other thing is the compensation filter, you're doing, that's angle dependent, right?
Okay.
So you looked at an angle dependent coefficient filter. You decided not to apply that.
Yeah.
You just have one that you apply to the entire thing.
Exactly.
And then you do the tapering.
Exactly. No, I did the tapering before, and I told the compensation filter, so to say, look, I'm applying the tapering window. Look, so the tapering applies to the modes, right? The orders.
Yes.
And the compensation filter is derived from the modes, from the mode strength. So if I apply the tapering already, when I derive the filter, I have the tapering already in what I'm looking when I derive the filter. Does that make sense?
Okay.
So I'm already compensating the tapering automatically, let's say, just by applying it when deriving the filter.
Okay.
I mean, if it helps, I'm not sure, but oh, this is very slow. Yeah. So this is the spherical scatterer, right? This is where we derive the frequency response from, and then we just look at the difference between a very high order and the truncated order. And if we introduce the tapering already here in the weighting of the mode strengths, then we already see it when we derive the filter. Right? So it's all relative. So it's already in there, so we're already compensating for it.
So if you know the order you want to truncate to, and it looks like the size of the sphere that you're using as a scatterer,
Yes.
you can derive the filter that you.
Yes, that's it.
That's all.
That's the only parameters.
Okay.
And actually, turns out that the dependency on the radius is not even that critical. It's pretty well behaved.
Okay.
Yeah.
Thank you.
So more global questions. So you have this high frequency loss basically only because you truncate from a high order to a lower order,
Yes.
right? So what's in the high order is the resolution of your HRTFs, right? You have stored these in a very high order.
Yes, but this is not dependent on the HRTF. This just happens in general if you limit the order of reproduction. If you limit the reproduction order, that's what happens. We looked at the case of an HRTF, yes.
Yeah, but it depends. I mean, it depends also on the encoding. So if you encode already a signal with just third order, then you wouldn't have this problem. Is that correct?
No, this is not correct.
No?
No.
The scattering effect itself is a high spatial frequency effect. As you saw, and even for the sphere, the scattering effect has high spatial frequency components.
Mm-hmm.
And if you can try to fit a third order directly, but you can't, you're averaging or you're smoothing over this high frequency. With third order, for example, you're smoothing over these high spatial frequency components, and that whenever you average over high frequency, you get get a high frequency rollover.
Okay.
Look at that, for example, right? This is not dependent on any HRTF or anything. This is just the pure inverse Fourier transform of the basis functions. So with the 30th order, you have all that high frequency. Well, this is space frequency now, but it applies to the time frequency too, right? You have all that high frequency ripple. And if you go to here, this is all averaged. So you lose all that high frequency content. Does that make sense? It's just averaged away.
I think you said you did try to just fit it directly to...
Yeah, I tried all different kind of stuff. It makes minor differences, like 1 or 2 dB. If you fit it directly to 30th order or to 3rd order, or if you fit it to a high order and just truncate. Yes, it makes a little bit of a difference, because in the end, how we obtain these coefficients is a least mean square fit, right? Yeah, so it will be slightly different. But this is not this is not the I would say the core of the problem. Let's say it's the core of the problem is not the fitting process. It's this frequency averaging in either space frequency and then of course in time frequency too.
So yeah, in practice, all this would boil down to is that you introduce one extra filter in your decoding, but that's just you can bake that into the HRTF or whatever you use for decoding. Right. So in practice, it doesn't have a real-time computational impact.
Yeah,
that's so you can do both the tapering and the compensation filter in that, or do you need to do the tapering separately?
I mean, the tapering amounts to one
just
multiplication for each sum of the orders. So that shouldn't, like even for 5th order or something, that's really just whatever 20 multiplications per frame. So that shouldn't be it.
Yeah, that shouldn't hurt too much. Yeah, and like all that filter business that I presented, it's not angle dependent, so you can just apply it before rendering. You can apply it in offline when you design the HRTFs.
That was the other thing. Like if we assume an application where we know the directions of the input signals, and that's where we started from, we could theoretically apply angle dependent filters because we know we're trying to render 200 sources and they're distributed in this way, and we could theoretically apply some pre-compensation filters. But it just turned out that those compensation filters we couldn't find a nice way of simplifying them so they wouldn't be as complicated as the HRTF. Then you might as well just use the HRTF.
Right.
Whereas this one is independent of, it operates directly in the spherical harmonics domain, so whatever sources you had, they're already there. Doesn't matter. And this can also then be applied to existing content.
Yeah, no, this is perfect. That's exactly what I need for my work.
Yeah.
As you know.
Yes.
Yeah, well, what I would be very interested in is how that differs for different fittings. Like, it will make a difference how you actually obtain the coefficients, how you obtain the spherical harmonics, right? And I just used what we have here in-house, which is a least mean square fit in the end. But there are other ways to do it, especially some pre-processing techniques that we just heard about yesterday, I think, right? So I don't know what happens if you apply these first, because you will lower the error and everything, right? But having said that, as I already told you, all that is not dependent on the fitting process. This is just purely because of the spherical harmonics itself, because of the reproduction side. So might be that we can gain even more when we tackle the encoding stage a bit more. You know, we can get even closer to the reference.
All right.